The line balancing problem consists in assigning a series of tasks to a series of stations. In this case, we have a company that manufactures amplifiers, which require a set of operations, these 12 operations, that should be done following or fulfilling some precedent requirements. For example, this PCB stands for the printed circuit board. This cannot be done if you haven't prepared the box first. Or this sixth task, which is connecting the two PCBs, this cannot be done if you haven't first assembled the power module and the preamplifier module PCBs correspondingly. So you have to decide where to do every task, and by where I mean in which station of the 4 they have at the moment, because they are redesigning an existing line of 4 stations. And the objective is to minimize the cycle time, which is the time in between two amplifiers being produced by this line. So the lower the value for that cycle time, the more productive the line is, the more outcome you get from the 4 stations you have. So that is the objective. And for that, in that playlist, I discussed how to do that by means of using an optimization model that looked like the one we have here, which is all these objective function with constraints and so on. And we saw how we can implement that into a software which we can use and get results. And we were assuming all along that all data is deterministic, in particular process times. So every time we have to do any of the previous tasks in any station, the time it takes is exactly the same, no matter what part we are producing. So amplifiers and all the resources involved are so that we can assume that this is the case. The time to, let's go back for a minute, the time to prepare the box, well, we cannot see that, but the time to put the cover, okay, is 3 minutes, no matter what amplifier we are assembling. But that is not always the case, but we will see that in a minute. The results we got from the optimization model is this. We have tasks 1, 2, 3, 5 performed in station 1, tasks 6 and 7 in station 2, tasks in station 3 are 4, 8 and 9, and finally tasks 10, 11 and 12 are performed in station 4. And that means that the time that we have an amplifier in station 1 is 3 plus 6 plus 7 plus 4, which are the durations of tasks 1, 2, 3 and 5 respectively, which adds up to 20 minutes per amplifier. The same goes for station 2, where we have 17 minutes or 19 minutes for station 3, and finally 20 minutes as well for station 4. The point here is that when we have that, we know that the cycle time for this line will be 20 minutes, because the pace of the whole line is set by the slowest of its stations. In this case, we have 2 that go at this very same pace, which is the slowest, 20 minutes per part. And if we assume, as we are doing, that times are deterministic, we know that this station will be working full time. So it won't rest, because the moment it has finished producing an amplifier or assembling an amplifier or performing these 4 tasks, it will turn in the amplifier to station 2 and will start all over again with another amplifier. As to station 2, things are different, because once it's finished, it'll have to wait 3 minutes for station 1 to finish its job. So it'll be waiting 3 minutes out of every 20, or on the contrary, or similarly, it'll be working 17 minutes out of every 20 minutes. That means a busy time of 85%. Station 3 will be working 95% of the time, 19 minutes out of every 20, and finally station 4 will be working all the time. And that would be the case if the assumption was true, or close to be true, because we might assume that these times we are adding here are always the same. But that might not be the case. That is what we are going to see in the next video.